educational videos by mmsprogramcivil.com. Please visit website mmsprogramcivil.com for all the videos. Basic design concept for doubly reinforced section. Doubly reinforced beam has reinforcement in both compression and tension zone. See in the figure below. This is the figure, right? This is the neutral axis. We know that above the neutral axis, concrete is in compression. So this is compression steel, and below the neutral axis, there is tension. So this is tensile steel. This type of beams can have rectangular or T or L shape cross section. When the depth of the beam is restricted due to requirement of headroom, space, appearance, etc., or when the design moment is greater than the uh, limiting moment of resistance, the beam has to be designed as doubly reinforced section. Okay, so let me show you in this figure. Say suppose this is the story height. Uh, this is the top of the bottom floor. This is the top of the top floor. And if we do not get enough head space over here, then it is necessary to restrict the depth of the beam. Okay. So many times the architect restricts the depth of the beam, and it so happens that the uh, design moment which we get from our analysis is found to be greater than or larger than the mu max, that is the balance section that carry. In that case we have to go for a design of a doubly reinforced section. The doubly reinforced section has following advantages. First, the reinforcement in compression zone helps in reducing the long-term effect due to creep and shrinkage. Okay, this reinforcement, which is placed in compression zone, takes the strain due to which comes due to long-term effect of creep and shrinkage and temperature, and so it is helpful in reducing the deflection, right? Okay, the compression steel also helps in resisting torsion up to an extent. We know that in case of torsion, that is twisting moment, we have cracks on the periphery, and at that time this compression steel which is provided at the periphery is helpful in resisting torsion up to an extent. Further, the compression steel increases the stiffness of the flexure member, and for large span beams, doubly reinforced sections are found to be economical than large depth singly reinforced beams, right? Okay. Then another important point is a spacing of stirrups in doubly reinforced beam should satisfy condition for both flexure member and compression member. Let me first show you the compression member. This is the compression member. These are the ties. Okay. If the diameter of the ties and the spacing of the ties are not as according to the codal criteria, then there are chances of buckling of steel, right? The same fundamental is also applied over here, because this is the steel in compression. If the diameter of the stirrup and the spacing of stirrups are not adequate enough, then there are chances that this steel will buckle, right? So which is not allowed. Okay, so that is why the spacing of stirrups in doubly reinforced beam should satisfy the condition both for flexure and also compression member, right? That is very important. Okay, uh, the maximum ESC in mm square that can be provided is 4% of the whole cross section. Maximum EST that can be provided is 4% of the whole cross section. Minimum ESC that can be provided is 0.2% of the whole cross section. Minimum EST provided is 0.2% of the whole cross section. And minimum dia of bar to be used both for ASC and AST should be 12 mm. The basic assumption made for singly reinforced flux member are equally applicable to doubly reinforced section. It should be noted that IS 456-2000 assumes the design stress strain curve for steel in compression and tension to be the same. This is very important, right? Okay. Behavior of doubly reinforced section. It has been seen that when the compression steel enclosed in stirrups is provided in compression zone, it undergoes tensile failure. It is even though the outermost concrete fiber in compression reaches its ultimate strain point 0035, the beam does not collapse but continues to take some additional moment. During this phase, the concrete cover spells and the compression steel may buckle and leading to the tensile failure giving enough warning. Okay. Usually the compression steel is kept close to the outermost compression phase, uh, leaving the least required nominal cover as is suggested by the code so that the stress in the compression steel is within the range of 342 to 354 Newton per mm square in case of Fe 415, and same principle is also applied for Fe 500 with an idea that the stress in the compression steel should be near to the design stress, right? In long term, the effect of creep and shrinkage increases the stress in compression steel and the steel in compression zone reaches its yield stress. Okay. IS 456-2000 states that the compression reinforcement must be enclosed by stirrups for effective lateral restraint. The spacing and the diameter of the stirrup should also satisfy the criteria for the ties in compression member to avoid buckling of reinforcement in compression zone. Okay, that is what I explained over here, right? Fine. Okay, now action of doubly reinforced beam. In doubly reinforced section, the design moment mu is greater than the limiting moment of resistance of the balance section mu max or mu limit, whatever you say, right? That means when the design moment is found greater than mu max, then you have to go for design of a doubly reinforced section. Okay. So additional steel is to be provided to resist the additional moment MA, where MU is the design moment is equal to MU max or MU limit, whatever you say, plus MA. So MA is your design moment minus the MU max, right? So that is your additional moment. Okay. So for to resist this additional moment, you have to provide additional steel, that is AST1. Okay. Now, when you are providing steel AST1, this will give us force TT. So force TT is equal to stress in the steel into area of the steel, and stress in the steel is 0.87 Fy because this steel yields before collapse, right? So the force TT is equal to 0.87 Fy into AST1. Okay, and moment additional moment MA will be equal to TT into this lever arm, that is D minus D dash. Okay. Now, to satisfy the internal equilibrium, we have to provide steel in compression zone which gives force Cc, which should be equal to force Tt. So that the moment Cc into this lever arm should be equal and opposite to Tt into this lever arm. Okay, so that is why to satisfy the equilibrium, we also have to give steel in the compression zone, right? So AST is equal to AST limit plus AST1, whereas ASC has to be provided in the compression zone to satisfy the equilibrium, right? Okay. So now D1 is the effective cover measured from the CG of the tensile steel, whereas D dash is the effective cover measured from the CG of the compression steel, right? This is D dash. Now the additional moment MA is equal to MU minus M limit, MU limit. MU is the design moment and MU limit is the balance moment for the balance section. Okay. Now this is the 3D diagram. Okay. This is your doubly reinforced beam. This is your balance section, and this is the additional steel that you have to provide for to resist the additional moment MA, and this is the compression steel that you have to provide to for the internal equilibrium, right? To satisfy the internal equilibrium. Now to find the depth of the neutral axis, okay, from the equilibrium we know force C plus CC is equal to T plus TD, right? Now C, what is C? We know C for rectangular section is 0.36 FCKBU into X max. CC is the force. So force is equal to stress in the steel into area of the steel, right? So stress in this steel is given as FSC minus 0.47 FCK, and area of the steel is ASC. Okay. Now force T is nothing. The stress in this steel is 0.87 Fy into area of steel is AST limit. So that is your T, right? And AST1, that is force TT is nothing but stress in the steel, that is 0.87 Fy into AST1 is the area. So that is your force TT, right? Fine. So now you can simply find x max. This is T plus TT. This is your C1, and this is your CC, and this is your C, right? Now the question comes in our mind that how to find FSC. FSC is the stress in the steel at the level of the compression steel. So for that, first you have to find the strain at this level, right? So we know this is the strain diagram. The maximum strain at the top is 0.0035, and the minimum and the strain at the level of steel is 0.002 plus 0.87 Fi by ES, right? So you can find the strain at the level of ASC by principle of similar triangles. Okay, this is D dash. D dash is the distance of CG of this ASC from the top, right? So using the principle of triangles, similar triangles, you can find uh, strain in the compression steel equal to this much by this formula. Okay. Once you find your strain, then you can find the corresponding stress. That if it is Fe415, you can use this table. That is for the known strain, you can find the stress. And if it is Fe500 for known strain, you can find the stress. And for intermediate value, you can do the interpolation. So this is how you can find your FSC, that is stress in compression steel. Okay. So after finding the strain in compression steel, you can use the table shown below for finding FSC. The final stress in the compression steel ASC is FSC minus 0.447 FCK, where FCK is deducted by a value of 0.447 FCK, which is the stress due to concrete area replaced by the area of compression steel ASC. Okay, so we are deducting this from FSC because when we are providing compression steel, okay, then we are removing some area of concrete which is equal to the area of steel provided, right? So when we are removing some concrete area, so the stress due to that concrete area has also to be reduced from the stress in the steel, right? So that is why we take stress in steel minus the stress in concrete which has been removed. So the final stress will be FSC minus 0.447 FCK. Okay, fine. So this is how we find C and CC1, C, CC, T and TT, right? Now, if the balance is a doubly reinforced, if it is a balanced doubly reinforced section, then we can find uh, the XU by D ratio by this formula, which we know, which is same as we used for rectangular sections. Okay, singly reinforced rectangular section. You can directly use this table, which is well known to us, that XU limit by D ratio is equal to 0.53 when it is when you're using FE250. When you are using FE415, then you can take it as 0.48, and for FE500 you can take it as 0.456, right? So there is an alternate method, or there is another table through which you can find FSC, that is You can first find the ratio of d dash by d. D dash is the distance, the effective cover, that is from CG of the compression steel to the top, right, or to the outer face of the concrete, and D is the effective depth, right? So for this known ratio, you can, and for the known grade of steel, you can get FSC from this table, and for intermediate values, you can do interpolation. Okay. Now, limiting moment of resistance. The limiting moment mu limit obtained from for the condition xu is equal to xu max is given below. Okay. When it is a balanced section, your depth of neutral axis will be xu max. Okay. So this is your doubly reinforced section. This is your strain diagram. This is your balanced section, and this is the additional steel required for resisting additional moment, right? So mu max can be obtained simple C into this lever arm plus CC into lever arm, right? See, this lever arm we know that is for rectangular section, that is d minus 0.416 xu max, and this is d minus d dash because this distance is d and this is effective depth d. So distance from here to here will be d minus d dash. So this is how we get this lever arm, right? So the lever arm for this is d minus d dash, and the lever arm forms for C is xu, I'm sorry, d minus 0.41 xu, right? Max, xu max, you can say. Okay, so we know now this is the equation we get. We know force C, that is 0.36 FCKB into xu max. We know the lever arm, that is d minus 0.416 xu max. Similarly, CC we know that it is FSC minus 0.447 FCK into SC, and this is the lever arm, right? So this is how you can find mu limit or mu max, whatever you say. Okay. Now area of tension reinforcement. So first for the balance section, we will find AST limit. Very simple. We know mu limit is equal to T into this lever arm, T into lever arm. We know T is 0.87 Fy into AST limit. We know lever arm is D minus 0 0.416 xu max. Okay. So you can MA is equal to mu limit, mu max is equal to this much, right? So AST limit you can say mu max divided by stress in steel into lever arm. Okay. Now how to find AST1? Okay, because total AST is AST limit plus AST1. Okay, so this is your additional moment MA. Now we know that MA is equal to force TT into this lever arm. Okay, and now TT is nothing but stress in the steel, that is 0.87 Fy, because the stress, we know that steel, this is tensile steel and it is going to yield. That is why we have to take the design stress, that is 0.87 Fy and into the area of steel, that is AST1. So this is the force TT into lever arm. This is the lever arm, right? So you can easily find AST1. So MA divided by stress in steel into lever arm, right? So you can find AST, that is AST limit plus AST1. Now next step is we have to find the compression reinforcement ASC. You can find the stress in compression steel using this table. You know your D dash, you know your D, you can find the FSC from this table, right? And you can use this equation, that additional moment is equal to force CC into lever arm, right? Force CC into lever arm. We know force CC is FSC minus 0.447 FCK into ASC. This is lever arm. So you can find ASC is equal to MA divided by stress in compression steel into lever arm, right? Okay. So now let us take an example. Problem number 1. Design an interior rectangular beam supporting a continuous one-way slab and supported on 230 mm thick masonry at on its both end, right? This is a one-way slab, right? Continuous one-way slab, and it is supported by this beam, and this beam is supported on 230 mm thick masonry wall. The clear distance between the wall is 6 meters. Okay, and The more weather conditions are moderate, and you have to use Fe 500 grade steel, and the thickness of the slab is 100 mm. Okay, and the live load on the slab is 3 kN per meter square. The beam has to carry a wall of 115 mm thickness masonry wall, right? And the size of the beam is restricted to 230 by 500, 230 by 500, right? So this slab is the span of the slab is 3 meters. So half the slab will pass on the load this to this beam, and similarly half the slab over here will also pass on the load to this beam, right? So first step is we have to find the effective span of the beam. And the effective span of the member that is not built integrally with its support shall be taken as least of clear distance plus d, or L center to center, right? Our beam is made up of RCC and wall is masonry, so they are not monolithic. Joint is more not monolithic in nature, and they are not integrally built. Okay, so we have to refer to this criteria. So given to us, B is 230, D is 500, and L center to center we know clear is 6 meters. This is 230 mm. This is 230 mm. So L center to center is 6.23 meters, right? Now weather exposure given to us is moderate. So for moderate condition, the minimum grade of steel to be taken is M25. Minimum nominal cover to be taken is 30 mm. So we can easily find the effective depth D. So effective depth D is capital D minus clear cover. So minus clear cover is 30. Diameter of the stirrup, we are going to use 8 mm dia stirrups, and minus diameter of the main bar divided by 2. We are assuming that we are going to use 16 mm dia bar as our main reinforcement. Okay, so 16 divided by 2. So this is how we get our effective depth D as 454 mm, right? So once you know effective depth D, you can find L clear plus D, right? So L clear plus D, the 6 meters plus 0.454 is equal to 6.454 meters. So we have to take our effective span as least of these two. So least of these two is 6.23. So our effective span is 6.23 meters. Now next step is we have to find the load that is coming on the beam. So self load of the slab. So 25 is the density of RCC, zero point 0.1 is the thickness of the slab, and 1.5 meter is the width of the slab. Okay, so 1.5 is the width of the slab. So this slab is passing its dead load to this beam, right? So we have to find this load on this beam in unit with a unit kilonewton per meter, that is UDL, right? So this is your 3.75 kilonewton per meter, that is the UDL that will be acting on the beam coming from the slab. Okay. Similarly, floor finish weight, we take 1 kilonewton per meter square into 1.5 is the width of the slab, and that is equal to 1.5 kilonewton per meter. That is UDL that will be passed on to the beam, right? Now dead load of furniture partition wall on slab, that is we are taking as 1 kN per meter square into 1.5 meter is the width of the slab, that is equal to 1.5 kN per meter. Dead weight of wall 115 mm thick, 20 is the density of wall. Okay, thickness is 0.115, height is 3, so this is equal to 6.9 kN per meter, right? Self weight of beam, that is 25 into 0.3 into 0.5, that is equal to 2.875 kN per meter. Live load on slab is 3 kN per meter square into 1.5 meter is the width of the slab, that is equal to 4.5 kN per meter. So this is what I have put in this table. One thing I have added is plaster load that can be taken as 1% of the dead load, right? Okay, now number of repeats. Now dead weight from slab. So there are two slabs, right? This is one slab which is passing on its dead load to the beam. This is second slab which is passing on its dead load to this beam, right? So there are two slabs, right? So the dead load is coming from the two slabs, right? Similarly, floor finish weight is also coming from two slabs. Similarly, furniture partition load is coming from two slabs. Weight of wall is one. Self weight of beam is one, and live load is also you can say it is coming from two slabs, so it is 2, right? So 1.5 is the load factor, which is multiplied by live load and dead load. So total load I get as 44.2625, right? So now I find the maximum moment at the center. This is simply supported beam. Span is 6.23. So WL square by 8, this is equal to 215.9 kilonewton meter. This is our design moment, okay? This is our design moment, right? Okay. So now we have to check for the depth, okay? The minimum depth to be provided to the beam is T limit, and that is okay, that can be calculated by this formula. This is your design moment. Factor K depends upon the grade of steel. We are having Fe 500, so K is 0.133, 0.133. So D limit is found to be 531.33, but we have provided 454, which is less than D limit. So the section is over reinforced. Okay. So in that case, over reinforced sections are not allowed. So either we will have to increase our depth, or we will have to go for design of a balanced doubly reinforced section. As the architect has restricted the depth of the beam, we cannot increase the depth of the beam. So we will have to go for design of doubly balanced doubly reinforced section, right? So let us start the design. Determine the area of tensile steel. We know AST required is AST limit plus AST1. Okay, for balance section we know XU limit by D. For FE 500 it is 0.456. So from that we can find XU limit, that is equal to 0.456 D, that is equal to 207. Okay, so this is your XU limit, or you can say XU max, anything, right? So once you know this, okay, so this is your MU limit. So you want to find uh, your MU limit, or you MU max, whatever you say. So you can take MU max is equal to C into lever arm. Okay, lever arm we know this is force C. Okay, and this is lever arm, right? So putting the values, everything we know, we get mu max is equal to 158.5 kilonewton meter, right? Okay, you can also find your mu max using this formula, that is kfc kbd square. K we have to take for Fe15, that is 0.133. So this is equal to 157.62, which is very near to this, right? A little bit difference is there in between these two, because K value I have rounded it up, so right. Okay, but we'll take this value in our design. Okay, so this is a table for where we find the value of K. So now you can find the ST limit, simple, that is equal to mu max divided by stress in steel into lever arm, that is equal to 990 mm square. Okay, we can also find AST limit using this table. From this table, you can find PT limit. We have M25 grade concrete and Fe 500 steel. The PT limit is 0.94. So PT limit is 0.94. So you can use this formula. AST limit is equal to PT limit into B into effective depth divided by 100. So this steel turns out to be 981.5 mm square, and this is 990. Slight difference is there because this is a rounded off value, right? Okay, so we will take this value in our design. Okay, that is AST limit is equal to 990, right? Now we will have to find AST1. Simple. Okay, so first we have to find the additional moment. So additional moment is mu max. Okay, additional moment is mu minus mu max, right? So our design moment is what, which we found from analysis, that is 215.9. Okay, and mu max is something which we found over here, that is for balance section, that is 158.5. so this both values we are going to take over here. Okay, this minus this is equal to 57.4. So this is your additional moment, right? So for this we have to find AST1. Okay, so before finding AST1, first we have to fix our D1 and D dash. D1 is the distance from the CG of the tensile steel to the outer face. So clear cover, we know nominal cover is 30 mm. Then it will be clear cover plus the diameter of the stirrup, that is 8 mm, right, plus half the diameter of the bar, main bar. We are assuming that we are going to use 16 mm die bar, so 16 divided by 2. So this is equal to 46, right? So D1 is equal to 46. Similarly, D dash we are also keeping as 46. Okay. Now we can find MA is equal to TT into this lever arm. Okay. Lever arm is D minus D dash, right? Now TT we know it is 0.8785 AST1. This is the lever arm. So you can find AST1 is equal to MA divided by stress in steel into lever arm. So this is equal to 323.416. So our AST required is AST limit plus AST1, that is equal to 1313 mm square, right? 0.416. Okay. So let us provide 225 and 216 mm diameter. So the steel area provided is 1384. This is area of steel provided. This is area of steel required. Okay. So that is fine. So once you know the area of steel provided, you can find PT. PT is equal to 100 into AST provided divided by B into effective temp D. That is equal to 1.325 percentage. Okay. So now the next step is you have to, so first let me show you the design in which we have provided two number of 25 mm dia bars and two number of 16 mm dia bars at the midspan over here, right? Because we are calculating the steel for the moment at the midspan. Okay, so this is steel required at the midspan. Okay, now let us find the compression steel. Okay, so compression steel is, again we have to take the same theory. Okay, so MA is equal to CC into lever arm. That, okay, that is what you have to take, right? Right. First of all, we will need to find FSC, right? So D dash we know, D dash we have found that D dash is 46, D we know is 454. Okay, so 46 by 454 is zero point 0.1. So for this, another grade of steel is 500. So FSC is 412. This is what we get from this table. Okay. Now again, MA is equal to CC into this lever arm, which is shown over here. So this is your CC. This is your lever arm. We know everything. So AC is equal to MA divided by stress in compression steel into the lever arm, right? So that is equal to 351 mm square. Okay, so we will be providing two number of 16 mm dia bars whose area is 402. So this is the compression steel provided, this is the compression steel required. Okay, so this is very important. Okay, so percentage of compression steel is found to be 0.385, right? You can also make some simple programs where you can give the overall depth of the beam, D dash, D1, B width, F5, FCK design moment, and here you can get the result. This is the EST required, that is 1313, which we got over here. Okay, 1313. Okay, required. This is required. Okay, this is also required, and this is the compression still required, that is 351. Okay, that is what we got, 351. Okay, so you can save time in doing calculation. You can use directly such programs. Okay, now this is the AC required, and we have provided 402, right? Instead of 351 we are providing AC as 402, right? So when you are providing steel more than required, then the neutral axis will move toward upwards, and that is good, right? As the neutral axis moves towards upward, the section becomes under reinforced. So that is very good. Okay. So it is good to always increase the area of compression steel than that what is required, right? So that the section will become under reinforced. Now we have to do the check for deflection. We know L by D max is equal to L by D basic into KT into KC. L by D basic for simply supported is 20. You know your percentage of compression steel is 1.325. Find the stress in steel. Okay, well, that is 0.58 into 500 is our Fy. This is the steel provided. This is steel required. This is steel provided. This is equal to 275.2, which falls between these two curves. And for this percentage of steel, you can find the corresponding KT. So KT is 0.87, right? Similarly, we know our PC. PC is 0.385. You can use this graph for finding KC. This is percentage of compression steel, and this you get KC as 1.1. Okay, so KC is 1.1. Putting all these values over here, we get this as 19.14. Our actual L by D is this is our uh, effective span. This is the effective depth, that is equal to 13.72, which is less than 19.14. So as this is less than this, so the deflection criteria is satisfied. Okay, that's fine. Now the next step is we have to see that the clear distance between the bars, as according to code, should be at least equal to the larger diameter of the bar. The larger diameter of the bar is 25. So the distance between the two bars should be at least 25. In our case, it is 230 minus 25 mm side cover minus 25 mm side cover minus 8 mm bar stirrup minus 8 mm die of stirrup minus 2 25 mm dia bar minus 16 mm 2 16 mm dia bar, and then divided by three spacings 1 2 and 3. That is how we get clear distances 27. So we are providing 27 mm instead, and minimum required is 25, so we are safe. Okay, so this is how we do the design of our doubly reinforced section. Okay, in this figure we can see this is theoretical cutoff, this theoretical cutoff. Okay, after this section, the moment in the beam is found to be less than MU limit. So this shaded portion has to be designed as singly under reinforced section, whereas this area is designed as balanced doubly reinforced section, right? So I hope this you must have found this video useful. Please visit website mmsprogramcivil.com, where all these videos are uploaded, and you can also see the PDF. Thank you.